and this fire gives pollutants of smoke, which are the sources of the pollutants in the building. And these pollutants are carried out by flow rate of air in the building. And the next one is a description of the fire spread in the building. In this case, we consider a building as a graph 2, and the branches of the graph are potential fire conductors. We consider 3 kinds of fire conductors: conductive fire conductors, for example, walls in the building between premises, radiative fire conductor, and verified fire conductors. This kind of fire conductors describes, for example, a flow of the hot gases between premises through a channel, through a ventilation system, etc. And to describe the ignition and fire spreading in the building, we consider an integral model of fire. And we have a choice to use a more complex model, but this model requires more time for calculation. But we go for another way. We use a very simple model, but this model allows calculating a big number of premises and calculating different situations which are different by conditions in premises, in environment. In this equation, the first term describes a heat exchange between premises. The second one is a heat exchange between premises and environment. T0 is the temperature of environment. And the third term describes a heat release in premises in fire. For conductive fire conductor, we consider a very simple model is a linear dependence. And for radiative fire conductor, we use Stefan-Boltzmann law. And we consider a different model of the premises. For example, the first one, a kinetical cell. This cell is a usual. This cell describes by Arrhenius law. And the second one is a constant rate of heat release and a constant temperature in fire. To illustrate the model, I show the result for calculation of the chain of premises. All premises are the same, have the same parameter, and we consider ignition of the one premises and spread of the fire from one premises to another. We consider non-dimensional variables, and we can see the results of calculation. This is the temperature of different premises. This is premises, the first premises after ignition, and we can consider the changes of the temperature in premises for different conditions. This model allows calculating a non-dimensional rate of propagation of the fire from premises. This is a parameter equal to inverse proportion of the time between ignition of the neighbor premises. And we can see that the dependence of the velocity of fire propagation as a function of the non-dimensional ignition temperature for different environment condition described by parameter epsilon. And we can see that the curves finished in some points. It means that there are no possibility to spread the fire in some condition. For this purpose, we calculate a limiting temperature of ignition below which the fire spread is impossible. Above this curve, the spreading of fire is impossible. Below is possible. And this slide shows our future plans. And thank you for your attention.
Thank you. Now, if you have some question, please.
First, good evening. My name is Rashkovskiy from Universitat Politécnica de Valencia. My question is about the expression you used to take into account the heat transfer with radiation. The expression you have put on the slide is applied only when you have two different surfaces and one of them is negligible compared with the other one. That's not the case, I assume, in the case of alpha building, because you have very large surfaces and they can have interact between them. You don't have negligible surfaces in this case. I think you must take into account the view factor as is normal in the radiation heat transfer. Okay?
I have shown the very simple example of calculation. In our model, we plan to use experimental data on correlation between different parameters of the premises and heat transfer between premises. And this experimental data can be included in the model and can be used for calculation of different scenarios of this flame spread in the building. Because of this, we can use experimental data. We can change a simple expression in the model by using more complex results of experiments and calculate a different situation in the building.
My question was only about the accuracy of the heat transfer expression you have used at the model. That's only the case.
Accuracy is defined by the expression which used in the model. For example, if you use experimental data and the accuracy of the method is defined only the experimental data which we use.
Well, I have a comment. For a safety point of view, yeah, you show something which is more or less an hydraulic calculation in the networks, in fact. And it is important to dimension the extractor, the ventilator, and so on. But another thing is the height of the layer in each room. So how can you perform such calculations? For the safety, it's important to know at each time for evacuation how is the height of the smoke in each room. So I think this is missing in your approach.
Of course, in this calculation we consider the situation in the room, for example, homogeneous distribution of the
yes, but it's impossible to have an idea and an estimation of the smoke layer with your approach.
No. This model is not considered layered spreading of the smoke in the building. For example, we consider the situation. In some premises we have fire, but there are a air flow in the building because we have open or closed windows and doors, and we have switch on air conditioner, and this one creates airflow, and this airflow carries out smoke in the building from some sources.
Yes, I understand, but how to predict the filling of each room? That's my question. So, okay. Thank you. Is there another questions? No? Okay.